long as you want.
As long as, you mean I can present as long as I want?
Yeah. Unless the presentation is annoying, and that is as little as we want. All right. It's Friday, so let's try to get through. A little bit of a rapid review of the ideas we're talking about Lasso. So the first thing I remind you, actually that's not what the definition is. So the first thing that I remind you is the definition of the subdifferential, like that, okay? So really we're looking for regularization terms that they're non-differentiable. So if we're gonna be talking about optimization, we need to be able to extend ideas from differentiable convex functions to non-differentiable convex functions. So we define the subdifferential as any g. So the subdifferential at theta 0 is any g such that this equation is valid. And graphically you can see at this point, right, the subdifferential will vary from the slope of this line here to the slope of that line. So anything in between. So that interval basically we defined as the subdifferential. And we gave an example, which actually this is what we need for Lasso. If you have the absolute value of theta and you try to define the subdifferential, if theta is less than 0, it's only -1. Greater is +1, and in between is -1 and 1. And the thing from all the key things that we needed is when you try to optimize, right, and you try to find the optimal of a convex function, you take the derivatives and you set it equal to 0. Here you cannot take the derivative and set it equal to 0 because the subderivative, it's an interval in general. So what you need to do is to evaluate if a point x0 is a global minimum in our case, you have to see if the 0 belongs to this subdifferential. Okay? So rather than the subdifferential being 0, you say, is 0 belong to that interval? Of course, if this is a differentiable function, this is just one value, and that statement is equivalent to say the derivative is equal to 0. Okay, we worked out the details for a very simple case that maybe I will repeat today, when x transpose x equal to the identity, and we concluded, if I can see it somewhere, that the solution Wj is given by this nice formula on the bottom. Okay? So if this xj transpose y are greater or equal to lambda, then the solution is given by xj transpose y minus the sign of xj transpose y times lambda. If lambda is greater than xj transpose y, and I want you to remember this because I'm going to use this. So if lambda is greater, for example, than all of this for all j's, all right, the w is the unit of 0, all right? But certainly wj is 0 if lambda is greater than x, than this absolute value of xj transpose y. So the nice thing we discussed was that somehow Lasso allows you to compute a whole regularization path. So not just, you know, fix one value of lambda and compute what the wj's are, but go even broader, start with lambda very small and take lambda to infinity, and you notice here, if lambda becomes very large, all the w's become equal to 0, and this is exactly what you see here. Something in case I miss it in the remaining of the lecture, right? In a very general problem, so this is a simple problem because we took x transpose x equal to I, but in a very general problem, the only thing you can observe here that you need to do is being able to jump from this point to that point, to that point, to that point, to that point. All right? You don't have to do anything in between because the solution is linear in lambda. So you can actually, based on computed geometric arguments, you can actually do this. So there are algorithms that will take you immediately from this point to that point, etc. So you don't have to waste any time in between because you already know what the solution is. Okay? And in this particular example, we discuss the active W's were only W1 and W3, and you can see here there is a whole range of lambda values where the only active functions are W1 and, the only active coefficients are W1 and W3. Okay, so let me correct now the equations to account for the fact that x transpose x is not equal to the identity. So the first thing that is going to change is this residual sum of squares when you take derivatives with respect to Wj has exactly the same form as before, but now I have kept this term. And so alpha j is given by this, and Cj is given like that. Okay? And you can see that Cj basically captures the correlation between the column xj and the residual, all right, using all the other futures but future j. It's very important, all right? So because we take derivatives with respect to Wj, what you actually get there is you get all the W's but Wj, all right? So this is the residual using your current futures, okay? So Cj captures how xj is correlated with the current residuals. This is very important because you remember it is the magnitude of Cj that decides which Wj at the end of the day is going to be 0. So effectively it's all related to what column is more correlated with the current residual. But bottom line is, right, so the first term in the likelihood term basically so it looks exactly like before, except this we did not drop the term x transpose x. So if you put things together, the only thing I want you to take note here, because I did not want to correct the slides, since these formulas are given in Murphy's book, I did not put on this sort of slides 2 lambda there. All right? If you remember, in the earliest presentation, I put a 2 lambda there, and this 2 and 2 and 2 are cancelled out. So I incorporated the 2 here, the 2 there, and there is no 2 lambda. Nothing changed, the same thing. Okay? So, so the subdifferential is equal to that. Okay? And when you take the derivatives of this, okay, which we have done already, you get this nice expression. So if Wj less than 0, you get this. Equal to 0, you get that. And Wj greater than 0, you get that. Bottom line, the solution is given by the equation for the very general case that you see on the bottom. If sigma j is less than minus lambda, you have this. Greater than lambda, you have that. And Cj between minus lambda and lambda equal to 0. Okay? And so can you actually see that if you take lambda to be the maximum of the xj transpose let me see if I can make the argument here. Well, since this is a little bit modified, so let me wait 2 slides and I'm going to make the argument about from where this is coming, okay? This is exactly as before, there's nothing new, but I wanted to emphasize something on the regularization path. Okay, so what I'm going to do is I'm going to take the solution that you see here on the bottom, and I'm going to write it in a compact notation so to simplify from now on the presentation. So we're going to introduce what's called a soft thresholding function that has 2 arguments. One argument is sigma j over alpha j, and another one is lambda over alpha j. And you can see here Cj over alpha j, lambda over alpha j are the arguments that I get. So this function is called the soft thresholding. It's given by this formula where this is the positive part of the argument. And I'm just going to plot this function. So the black line that we see here is Cj over alpha j. And I can tell you that's actually the least square solution for Wj. That's the black line. And the Wj that we get from Lasso, which is from here, corresponding to this soft thresholding, is basically this red line. So you can see in between minus lambda and lambda, the coefficient Wj is set to 0, but also you see the larger lambdas, the coefficients that they are not zero and they are big, all right, the w's that they are big, positive or negative, are also shrunk towards the zero. And in some sense, this is not very good, right? So we need this for sparsity, but also there is this effect that introduces bias in the Lasso simulation. Okay? Later on, in a few slides, I'm going to show you some results that are using what's called an unbiased Lasso simulator. So you can maybe think of a modification to the Lasso algorithm where you do achieve this soft thresholding and these coefficients are set to zero, but maybe bigger coefficients are not shrunk towards zero. So somehow you can think of a correction where this thing is not happening, all right? And that is called the biased Lasso formulation that we will not discuss in details because we would need a whole hour to go through it. Now, this hard thresholding looks like that, okay? So this is the least squared solution. And again, this looks like the unbiased thing that I mentioned. So effectively, you set the coefficients to zero, but actually you don't touch upon the rest of the coefficients. Okay. So if lambda is greater than lambda max, where lambda max is defined by this, the argument here is that W equal to zero, all the W's. You remember that from the analysis we did yesterday? That if lambda is greater than lambda max, all the W's are equal to zero. In the context of what we discussed yesterday, right? We did not, we were playing with this column xj transpose y, all right? And when lambda was greater than the maximum of those, everything was equal to zero, okay? So effectively, when you want to start the Lasso algorithm, it's not a bad idea to start a little bit higher than the lambda max. So, and if you use actually the original Lasso software by the developers, you will see that's what they use, okay? So you put a lambda a little bit higher than lambda max, and then you start reducing lambda, so some of the coefficients become suddenly non-zero, and that way you form the whole regularization path. If you want to write this more concretely, for the very general case, lambda max is the maximum of the gradient of the negative log argument. Okay, so that's what lambda max is. So let me summarize for the case of x transpose x equal to I, all the algorithms that we have seen starting with least squares, okay? So if you write the residual sum of squares, you set x transpose x equal to I. The reason actually, not only we simplify the algebra by taking x transpose x equal to I, but actually we are making each of the futures independent, right? So we can actually compute each of the wj's independently. So for that case, the MLE estimate for the coefficient k, which is ordinary least squares, is nothing else but the k column of the x matrix times y. That's ordinary least squares. The ridge regression, which is, the root, it's minimizing basically the residual sum of squares plus an L2 regularization term, is this estimate divided by 1 plus lambda, okay? And the Lasso formulation is given like that. And then, you may see in the literature what is called a subset selection, where you actually decide, when you do ordinary least squares, you decide how many coefficients to keep, and you say, I'm only going to keep k of them, and I'm going to set the rest equal to zero. This is what is called a subset selection, and sort of not very much different from this concept of hard thresholding. Okay? But remember these formulas because I'm going to use them, right? So ordinary least squares, ridge regression, this is the Lasso, right? So this is the soft thresholding function that we discussed before, okay? And in some sense, you can see the ordinary least squares term is needed because I remind you the ordinary least squares term is nothing else but Cj over alpha j. Okay, that's what you get with least squares. Okay. This is an example here from a book from Hayes' book. By the way, this book, it's sort of like the Bible, or it was the Bible in statistical learning for many years before Bishop's book. And it still contains extremely novel ideas. It's less Bayesian than, actually way less Bayesian than Bishop's book, but the ideas contained in this book are in many ways unique. And you can download the most recent version and lots of software electronically from the author's website, hopefully under that link. Okay, so let's go back to the regularization path. I don't know if I should repeat these things, okay? I mentioned before, actually, I wanted to make this argument. If lambda is greater than the maximum over J of the xj column transpose y, then all the w's are equal to 0. And the way, if you want to check right these arguments, you know, it's like saying the optimal solution is w equal to 0. So for this to be optimal, the 0 needs to be contained on the subdifferential for the case lambda greater than that. So if you take the subdifferential, it's given by this, and if you say the 0 has to belong to that, means the 0 has to be greater than minus this minus 2 lambda, and then the 0 has to be less than minus this plus 2 lambda. Okay? And if you put the two things together, so for the 0 to belong to the subdifferential, lambda has to be greater than that, which is the case. Right? Simple proof. So if lambda is greater than the maximum of xj transpose y, all the w's are equal to 0. So in general, to get a sense of how the algorithm will work, right, you can think if you take x transpose y and somehow you put in order of magnitude these inner products, y transpose times x1, y transpose x2, let's say is the second largest, y transpose x3, the third largest, and you start from a lambda that is higher than that, where all the w's are equal to 0, and you start reducing w. So the first time, when you reduce w, when you reduce lambda, that lambda would be less than that and greater than that. We agree? Because this is the greatest value. So once you cross that value, you will see a change. And what is that change? The first element of w is going to take a non-zero value. Everything else is going to remain 0. Why everything else is going to remain 0? Because lambda is greater than y transpose x2 and also y transpose x3, y transpose x4, because we order these inner products. Okay? And again, you can prove here, right? So tell me how this proof goes, right? You can prove that if lambda is between those two, then all of these things except the first element is 0. Look at this proof and tell me how it works. So why when lambda is, so we use lambda is between y transpose x1 and y transpose x2, why all of these things are equal to 0? What do we need to do to prove that? I mean, to prove that all of these w's is the solution, we need to prove for all of these w's being 0, the 0 value belongs to the subdifferential when w equal to 0. And the subdifferential looks like this. Where is the subdifferential? If you look for w equal to 0, the subdifferential is minus 2xj transpose y plus 2 minus lambda lambda. So we need to prove that the 0 belongs on this interval, which means we need to prove that lambda is greater than y transpose xj for j not equal to 1, right? We look at these rows here. But that's true because lambda is less than x1 transpose y, and is greater than all the other x transpose xj transpose y. Does that make sense? Do we follow how the argument goes? Since we don't, can you convince me why this is a solution for W1 when lambda is between this and value and that value? Tell me why, where do I get this value that you see there when lambda is between this value and that value? What do I need to do to prove that's the answer? What's the logic? We have the solution, the subdifferential here, so what do we need to prove? So in this case, right, this is a value, it's not an interval, so we're going to have to set it equal to 0, okay? And so this is equal to identity here, so we're going to have Wj equal to x1 transpose y, all right, minus lambda, divided by, no, actually I can do this in general, divided by x1 transpose x1, so I don't take this identity, okay? And this is what I get, right? You set this equal to 0 actually, and maybe I should not even write it like that, okay? Because this is single value. I should take this thing, and instead of saying 0 belongs to that, I should write this equal to 0, this equal to 0, and there's the answer for W1, okay? And by the way, you can see, I use the formula here, I assume that W1 is positive, and indeed, the answer that I get gives me W1 positive. Why? Because lambda is less than y transpose x1. You remember we moved lambda to be less than y transpose x1 and greater than all the other y transpose xj's. Okay? So can you tell me now what is going to happen if I move lambda between y transpose x2 and y transpose x3? Add another element, and you can actually keep going, right? And I thought I was showing it, but anyways, keep going like that, and as you reduce lambda, basically all the w's will become non-zero, and you're done. Okay? So you can, here is L2 regularization, right? This is ridge regression, and you can see on the left that the regularization parameter is high, so all the coefficients drop to 0. You can see the differences here with Lasso regression. So when you start with very high regularization, all the parameters are equal to 0, but when you hit, you remember x1 transpose y, one of the parameters becomes non-zero, then when you hit another value, another parameter non-zero, and keep going like this. So you build the whole regularization path literally at a cost that is equivalent to running one discourse problem. So this is very significant, you know. Here, if you try to build this diagram, you're going to have to run a lot of discourse problems here with one model, basically, and one sort of evaluation. We can get the whole regularization path. And as I mentioned, you don't really need to play with lambda in between these subintervals, because nothing happens in between. Everything varies linearly, so you know the answer. Okay. So the algorithm basically goes under the name Lars, and so you should know this. And let me only mention this little statement there. If, let's say, that the number of input futures D is way higher than the number of data, then as you expect, you will get at most n non-zero W's when you do Lasso, okay? You're not gonna be getting more than n W's basically in your model. So if you really want, you know, if D is like 1,000,000 and n is, you know, 5,000, and you want to get more W's than n, then what you need to do is you need to modify the Lasso algorithm, and you need to use what's called elastic Lasso, where simultaneously you use L1 and L2 regularization. And actually that is a way more popular algorithm. So keep in mind there is Lasso, and then there is 50 different versions of Lasso to address every problem Lasso has. And maybe if one of you is interested, you can do another PhD thesis on another Lasso version that addresses pathologies that someone has not had time to think yet about. Okay? And of course, we already talked about the unbiased Lasso, right? That's a very significant modification. And it's actually a minor modification to the overall Lasso algorithm. By the way, if you're going to use the Lasso algorithm, don't download anything from the web. There is only one Lasso algorithm, which is the one directly from the author's website. And I think that is the state of the art. And then you can run a lot of the examples they have in their books, and they give the data set so you can play with that as well. All right. You remember I introduced, I think yesterday, one simple example where I created data through a regression model, right, through a Gaussian, effectively, with some sparsity in W's. So we started with a model that we knew what coefficients W are non-zero. And then the idea was, can you actually discover through Lasso the exact source of sparsity in the model? And I mentioned that's always not possible. Okay, it's not a trivial thing. And in some sense, everything we have discussed on this course, right, and in machine learning, you really want to have very good generalization capability. You need to be able, for a new X to tell me what Y is and what the uncertainty on Y is. There is no emphasis on being able to find the exact sparsity in the model. What does that mean? Because that's in your training data, and you won't have good predictive capability. So the two things are not consistent. Okay? And if you want to actually, if you have a model that on the limit of infinite data captures basically the true source of sparsity in your data, this is called, your model is called, the model selection that you do is called consistent. Okay? But this only you can hope will be the case when n goes to infinity. So this is a very nice example if you want to run it from Murphy's book. Okay, so what he does is let me go back to read the whole problem. He generates a matrix with 1,024 points. The points have dimensionality similar to what I discussed before, of much higher, 4,096 dimension. And so the way the data generated through, you can imagine here is a Gaussian model, we take a sparse W that only has 160 non-zero values, all right? So many of the W's are zero, very sparse, okay? And those non-zero W's, we put them plus minus one values, okay? So this plus minus one spikes. So what you see here is all these 4,096 values, okay? And you can see these are the W parameters, plus one, minus one, plus one, minus one. So if you use your standard Lasso, it seems very nice, sparse, but actually you don't learn the actual model that generated the data. The plus minus peaks don't correspond between the first picture and the second, okay? If you actually try to do, rich regression, least squares basically, you don't learn anything sparse in the model, so all the values look basically, everything is non-zero, okay? If you try to do the biased Lasso, where basically the only difference from your classical Lasso is not to penalize the coefficients W that they are big, right? You remember, everything is dropped down towards, it shrinks towards zero, so if you don't do that, you can see actually that the peaks you learned, they are not very much different from the true model. So this is really the way to go for this type of problems. But again, most probably if you look very carefully, not everything is perfect. I'm guessing, right? It looks very good, okay?
It has a
You see some differences somewhere?
There's somewhere we have the problem for the homework. Sorry. The misclassification accuracy is very low.
Okay, yeah. So it's a very good, and actually you can see the mean square error is extremely small, it's 10 to the minus 5. Okay. Okay. Now, obviously, we started talking about this the Bayesian version, right, with different priors for this binary variables gamma j. Really, if you want to address all pathologies, you really have to become fully Bayesian, and there is a Bayesian Lasso actually version as well. Okay, so don't get excited that you will work on a Bayesian Lasso because people already have done that. Okay, so that has already been done. And so the Bayesian Lasso algorithm is called Lasso. Okay, and actually what I mean, this is slightly non-Bayesian. What they are doing is, right, so you're trying to calculate in some sense these probabilities, all right? So you say, should I include the j variable in the model or not? So the idea here is, the classical way of doing this is to do cross-validation, right? To use another data set and try to calibrate your probabilities. The other way is to actually run the Lasso algorithm for different data sets and then find out how many times the variable j was included in the model. And you can put a threshold and say, look, I'm going to run it for 10 data sets. If 90% of the time variable j is in the model, then variable j is in the model. Okay? Obviously, this is an enormous waste of data, but you notice at least in the training of Lasso, the calculation was straightforward, so it's not like there's a significant cost there. And so people already have done this, right? This is what goes under the Lasso algorithm. And I cannot read the first two diagrams, so you're going to have to tell me what it says there. So the whites here, let me see. So this is the regularization parameter, right? So the whole regularization path. High regularization here. So all these coefficients are 0, black is 0, white means they are non-zero, okay? And this is the probability of inclusion of the different parameters in the model, and each of these lines corresponds to a different data set that you use to train the model, okay? So, and the number of data realizations that, that was tried for this problem varies basically from 2 to 256. Okay. All right, so we have 15 minutes, so let me start discussing now about ideas from gradient descent, which are more popular today, and how they can be relevant to L1 regularization Lasso type of algorithms. So remember, if you want to compute Wj, all right, effectively, you really have to solve this minimization problem. You say, I'm going to take a perturbation of Wj by Zj. This is like a directional derivative. You set this, you minimize this, and that's the new Wj star. Okay? So we'll see how this type of ideas can be explored in the context of Lasso. So for now, let me just give you how the algorithm basically looks in a few lines. Okay? So, and there's no regularization path here, so we fix lambda. This is your least squares W, so you start with that. And you remember for every j, what you need to do is you need to compute the alpha j, you need to compute the sigma j, and then if you have a function already programmed for this soft thresholding, you set each of the Wj is equal to that, and you continue this for all d, and you're done, okay? And I think we will see this algorithm. So of course you can do a repeat this over lambdas, and then you can do repeat this over data sets, and you can get all different versions of the Lasso algorithm. So we need to use gradient descent methods, right? And the idea here is in the gradient descent methods, somehow we're going to have, even in exploring basically the regularization path, we need to take advantage of the similarities between the W calculated before with regularization parameter lambda k minus 1 to the W when the regularization parameter has changed a little bit. Okay? So somehow you can think of an approximation we're going to be doing around this value to allow us to compute in general that value as an optimization problem. I want to go directly to the substance because we're not going to have time to discuss everything. So let me introduce notation of these things. Nothing new yet. So our objective function, you remember, is the negative log likelihood. That's the residual sum of squares, let's say, plus a regularization term. All right, so I will explore all possibilities and I will try to unify different approaches to this problem. But for Lasso, this was the L1 norm. For ridge regression was an L2 norm, or we already saw the L0 regularization. So we will try to see, can we actually optimize this problem in the general case where R of theta is non-differentiable. Can we use gradient descent methods to actually compute theta in this case? So the Lasso problem, equivalently to this, can be written like that. Remember I mentioned this on Tuesday? If you want to minimize this, is the same as minimizing that with this constraint that theta 1, the norm 1 of theta is within a ball in norm 1 that defined by radius b, where b is related to the regularization parameter you use in R of theta. This is not an approximation, it's exact. For every lambda you use in a regularization, there's a corresponding b. And you know what? You can, in many ways, you can think of this problem as being the dual of that, right? So here we say minimize this plus some regularization. Now you say no, minimize another regularized problem, but with this constraint. So this is sort of the primitive form. And the constraint here, if you define this as a set C, all right, the penalty introduces if theta belongs to this constraint, the loss function is 0. If it doesn't, it's infinity. Okay? So minimizing this can be written exactly in this form, and I'm going to take advantage of mathematically of this form to do optimization. So let me give you an idea of how you can start thinking of optimization on this. So what I have here is I have my R of theta term, all right? That's my regularization. And I have done some simplifications on the residual sum of squares. So basically I dropped everything except saying, you know what, make theta as close as possible to y. So this is not a regularization term. This, just to simplify things, and I'm going to modify it in a few slides. Just to simplify things, I am saying take this residual sum of squares as this term that says make theta as close as possible to y, but also satisfy the constraint implied by the regularizer. So computing theta that minimizes this can be written down using what's called the proximal operator, and the proximal operator of y for a set R is defined as this, is the argument z that minimizes this function. So effectively you say, find me a z that is as close to y, all right, and that minimizes the regularizer R of Z. We have reversed a little bit because we simplify the log likelihood term here, right? I am saying, find me a Z that is close to Y is data, let's say, and at the same time minimizes R. And this operator is called the proximal operator of Y for the set R. And you may say, what am I learning with this? What we're learning is the following. We're learning that there is a new way to think on these optimization problems with proximal operators. And why is that good? Because you know what? This problem has exact solutions for many different versions of R. Because people have worked out on the mathematics of this problem. So if you have something like that, and you want to compute this for a given R and a given Y, people have an exact solution to that, and I'm going to give you some examples to that. So for example, if the regularization is a Lasso regularization, then the proximal operator of theta for the set R defined by this is really the soft thresholding function theta comma lambda. Okay, and you can actually prove it. This is the proof is no more than half a page for this. Okay, you can prove that if your regularization is defined by the 1 norm of theta, this problem has an exact solution given by this soft thresholding function. If the regularization is L0 regularization, you can prove actually that the proximal operator is a hard thresholding function here. You can see basically in between minus square root of 2 of lambda and 2 square root of 2 lambda, this it's set to 0, and outside it's set equal to theta. So you know, basically in the interval minus square root of 2 lambda to 2 square root of 2 lambda 0, and then away from that it keeps the actual values of theta. So that's hard thresholding. If this R of theta, you see this defined as an indicator function. So if you say R of theta is the indicator function that theta belongs to a set C, okay? So this is basically 1 equal if theta belongs to C, 0 otherwise. Then the proximal operator is nothing else but the projection of theta to the set C. Does it make sense? Right? If somebody tells you, find me something that is as close to theta, but it also belongs to the set C, the only thing you have to do is find the projection, the nearest point in the set C where theta is projected, right? That's the projection operator of theta in C. And if you want to get a common sense sort of an example of what that means, if you have this, if C is defined by this constraint, so if theta j, let's say, is between Lj and Uj, if your theta is to the right of Uj, all right, if the theta is to the right of Uj, what's the projection of theta? What is the closest point on this set that you can project? Is Uj. If theta is to the left of Lj, what's the closest point? Is Lj. And if you're in between, you don't need to project because you're already satisfying the constraints. So the answer is theta j. Further examples. If you have a hypersphere in L2 with a unit radius, and you want to use this calculation and you want to project the point theta to the hypersphere, if you're inside the hypersphere, what's the projection? No projection because you already satisfy the constraint, so the answer is theta. If you're outside the hypersphere, what do? You basically have to take the radius and project to the sphere itself, so it is theta, so you are in the direction of your vector theta divided by the magnitude of theta. Okay? The point here is, right, that all of these problems with this proximity and projection operators, basically, all of them have analytical solutions for many different types of regularization terms R of Z. The most difficult, of course, is in the context of Lasso, if the set C is defined by norm 1, right, the way we are dealing with Lasso, then the proximity operator is this soft thresholding function, okay, when lambda is equal to 0, if it says, so if you're inside the constraint, okay, you don't need to regularize basically, right? That's the idea. And the answer is basically given by what we have seen before. But if you're outside and you need to project, then basically you have to solve this equation to compute lambda, and the solution is given by this formula. It's soft thresholding, but lambda is not arbitrary. Lambda is the solution of this equation. And there is a little computer program actually to solve this equation for a given theta to find lambda that you can read more from this reference. And again, you don't need to remember this. Obviously, this soft thresholding, the hard thresholding, the classical projections, operators, just remember in general context what they mean, and that we have analytical solutions for all these problems. All right, so let me, we have 4 minutes. In case nothing sort of clicked and why we do this, let's go back to the real problem. Remember, in the real problem, we had some regularization, okay? And in our case, L1 regularization, and then we had the negative log likelihood. So what I have done here, I expanded the negative log likelihood to Taylor series expansion literally to L calculated on the previous estimate of the parameters, plus the first order term, plus the second order term, where 1 over tk gives me basically an approximation of the Hessian. So I don't have to compute the Hessian exactly, okay? But what I have done again is, I wrote a quadratic function, if you like, for the log likelihood, okay? And I'm asking, minimize this function for different regularizers and tell me what the new update of the parameters theta is if I know where I am right now. Okay, so if you know theta k, compute what theta k plus 1 is. So g is the gradient, all right? And 1 over tk is an approximation of the Hessian. So what you can do is, because we want to do a minimization in the, with respect to z, anything that does not depend on the z, you can get rid of them. And you can see if you combine this term and the linear term from there and the quadratic term in z, you're actually going to get minimization over z of a function that looks like this. Okay, so tk times r of z, obviously that makes sense. And then these two terms combined, you're going to get the L2 norm of z minus uk, where uk is theta k minus tk gk. Does this remind you anything, by the way, this step here? Tell me, what does it remind you? What algorithm optimization theory that step uk reminds you? tk, it's an approximation, you know, actually 1 over tk is an approximation of the Hessian, so tk, it's the Hessian inverse. So what does this step remind you? What algorithm in optimization? Newton's method. All right, so this is Newton's method, okay? So, so what you're asking now is compute the z that minimizes this, but in some sense, what that means is find me a z that is as close to uk as possible, and at the same time, right, minimizes tk times r. That's the proximal operator defined for uk, with the set being tk times r. And there is an analytical solution to that problem, as we have seen, for very many different regularization terms out. Okay? So if you take the regularization term r to be 0, you basically get gradient descent. You just told me you recognize Newton's method there. If you take this r of theta to be basically the indicator that you belong in a set C, you get it what's called a projected gradient descent. So your solution always has to be satisfying the constraint. And if r of theta is lambda times theta norm 1, right, the Lasso way, you get an algorithm that's called iterative gradient descent. And so you can try different things and you can generalize this. Okay, so let's do the projected gradient descent. I have to finish immediately after the picture. So let's say this is the feasible set, right? If you do a Newton, you are at this point in the parameter space, you are moving with a Newton step. There is a tk missing there, but it's okay. You know, you are moving to theta k minus gk. That point's outside the feasible set. So what you need to do is project this point to the feasible set. So let's say this is the projection, and so you move from theta k to this projection. So if this point is theta k plus 1, your next move is basically the step that you take is theta k plus 1 minus theta k. If you ask about what do you do with tk, because that was an approximation to the 1 over tk was an approximation to the Hessian, but actually you can do a very easy calculation using only the gradients of g. So you can find, if you set 1 over tk equal to alpha k, you can find alpha k by satisfying this equation, right? It looks like the gradient of the gradient that will give you the Hessian, and you can solve alpha k using least squares. And if you do this, this is the Barzilai-Borwein formula, and this formula, if you integrate it with this iterative soft thresholding technique for the, with this norm, and if you integrate this continuation method allows you to explore the whole regularization path, you get an algorithm called sparse reconstruction for separable approximation. And the algorithm is actually a few lines, extremely powerful. It allows you to do Lasso for all lambdas using basically steepest descent type algorithms. And if you go and look, and we will come back on this briefly on Tuesday, the